Hello. So far we have discussed the about unit number 4. So that was as such related with the steam turbine. We are now moving towards the last unit for our subject, that is the unit number 5, that is entitled as the gas turbines. In the steam turbines we have seen that the steam is nothing but the working fluid which operates the turbine. As compared to that one, instead of using the steam as a working fluid, the gas that is used for the operation of the turbines, hence we identify them as the gas turbines. The points which are of interest to us, which can be focused for the gas turbines, so that includes the working principle for the operation of the gas turbine. What are the different wide areas of applications where the gas turbines are popularly used? It is also interest to us to make the comparison on the various points how the steam turbine that differs from the gas turbine as far as the various aspects are concerned, maybe construction features, it may be the operating principle, it may be the advantages and limitations of the steam turbine and gas turbine over each other. We'll be looking into the different gas turbine cycles. Popularly, the two different cycles are used for the operation of the gas turbine. One that is called as the open cycle gas turbine, and another that would be called as the closed cycle gas turbine. The gas turbine they operate on a thermodynamic cycle, and that thermodynamic cycle which is used for their operation. So that cycle is called as the Breton cycle. That cycle is known as the Breton cycle. We will see what are the different components for the operation of this Breton cycle, which different thermodynamic processes are involved so as to complete the cycle, and the representation of all those thermodynamic processes on the pressure volume as well as the temperature entropy diagram. This pressure volume and temperature entropy diagram that help us to carry out the thermodynamic analysis of the Breton cycle, which indeed we will be interested to determine the equation, to find out the equation for the calculation of the thermal efficiency for the Breton cycle. The thermal efficiency of the Breton cycle that will be essentially initially looking for a simple gas turbine cycle consisting of some fundamental or the basic components. But the story can be further extended if we are interested to increase the efficiency, improve the efficiency of the basic gas turbine cycle. Then definitely we should look for some alternatives, some modifications in the cycle, alterations in the cycle. So those different components which are arranged in the modified cycle, so those are essentially used for the performance improvement, and such methods, such arrangements, mechanical arrangements, they can be called as the performance improvement methods in the gas turbines. And as far as our subject matter is concerned, so we'll be focusing on the three different methods for the performance improvement. First method that we'll call as an intercooling. I am confident that in your earlier semesters, specifically in semester 4, that you might have studied about the in the applied thermodynamics, the operation of the compressors and the work which is required for the compressor that can be reduced by using an intercooling arrangement. So same intercooling arrangement that can be also utilized in the gas turbine power plants to improve the efficiency. The another method that is of interest to us, so that would be identified as an reheating, and the third arrangement is nothing but the regeneration. So these three arrangements, namely intercooling, reheating, and the regeneration. So these arrangements are specifically used for the performance improvement over the simple gas turbine cycle. And toward the end of this particular unit number 5, we'll be quickly having a look for the different fuels which are used for the operation of the gas turbine cycles. Okay, so all these are the points which are of interest to us. This particular photograph that shows the picture or pictorial representation of a big size gas turbine power plant. Coming on to the working principle for the gas turbine power plant, I would like to draw your attention here for the diagram which is as such shown at the bottom. So that essentially consists of the three different components, three different parts I can say. The first one that is nothing but the air compressor. Next to that one, it is the combustion chamber, and toward the end, it is nothing but the turbine. So I can say that the gas turbine that consists of the three important mechanical components: air compressor, combustion chamber, and the turbine, a gas turbine. The air is compressed to a high pressure by the compressor. Okay, so we can see here that the air intake. So air will enter into the turbine at the atmospheric pressure, and the work will be done on the air to increase its pressure from the initial level to some desired pressure, high pressure. This high pressure air will then get admitted into the combustion chamber, where the mixing of this compressor air will take place with the fuel, and there would be a suitable source which will help us for the ignition or the burning of the fuel in the combustion chamber. The burning of these gases in the presence of the air that releases tremendous amount of energy, thermal energy, and these hot gases are then given off to the turbine, which causes the rotation of the turbine wheel or the turbine rotor, we can say, and thus it develops the mechanical work. It can be also seen here that the turbine and the air compressor, so they are mounted on the same horizontal shaft, right? So this is what the simple means by which one can give the working principle for the simple gas turbine power plant. This particular block diagram that shows the arrangement for the gas turbine cycle. Here we have the compressor, air compressor, and this particular region that shows the atmospheric air, surrounding air that is drawn into the compressor. High pressure air that leaving the compressor enters into the combustion chamber. We burn the fuel. Gases are then admitted into the turbine, which performs the mechanical work after the expansion, and the gases are exhausted to the atmosphere, to the surrounding. And this is what the horizontal shaft, and on either ends of the shaft you can see the compressor is there placed at the left side, left portion of this particular arrangement, and the turbine that is placed on the right hand side of the arrangement. Okay, so this is nothing but the simple way by which one can represent the block diagram for the gas turbine cycle, consisting of the basic components: compressor, combustion chamber, and turbine. This is the pictorial representation, three-dimensional view for the compressor, combustion chamber, and the turbine. And whatever this horizontal circular one that one can see, so that is nothing but the shaft of this entire arrangement. Coming on to the wide areas, tentative areas where the gas turbines are popularly used, that is applications of the gas turbine. So they are commonly used for the operation of the pumps, for driving the different types of the pumps, for the operation of the compressors. They are commonly used in the high speed cars as well to get the rapid acceleration. The major areas where this gas turbine find their popular place are nothing but the propulsion of the aircraft engines, as well as propulsion for the engines which are for the ships. So not only these two areas are commonly used for the applications of the gas turbine can also be used for the generation of electricity. So that is nothing but for the power generation. The features of the gas turbine power plant that makes them a suitable candidate for subjected to the peak load requirements. Additionally, they are also suitable as a standby unit. So these are the some of the wide areas of applications for the gas turbines. As I have mentioned that the two gas turbine cycles, those are important to us. We'll focusing on one of the cycle, that is the open cycle gas turbine, and another is nothing but the closed cycle gas turbine. The block diagram which can be seen here on the left hand side, so that is there as such for the open cycle gas turbine, and we see here a compressor, a combustion chamber, and a turbine. Compressor and turbine, they are mounted on the one horizontal shaft, and the different state points can be also seen here. Okay, state point 1, state point 2, state point 3, and state point 4 respectively. The state point 1 that shows the condition of the fresh air, or that is nothing but the atmospheric air at the atmospheric pressure 1.01325 bar. Okay, so that is nothing but the inlet condition for the air to the compressor. State point 2 that represent the condition of the air that leaves the compressor or enter the combustion chamber, that is after the compression. Point number 3 that represent the condition of the hot gases entering into the turbine, high pressure, high temperature gases at the inlet of the turbine. And condition number 4, state point number 4, that indicates, that shows the state of the gases after utilizing their energy and they are exhausted to the surrounding, right? At the other end of the turbine we can see that the W net, so that is the thing but the network which can be obtained from the gas turbine power plant, right? So that is what the description for this open cycle gas turbine power plant that can be mentioned. A point-wise description for this arrangement, so that can be seen here. Gas turbines are very popular. They usually operate on the open cycle. Air at ambient condition that is taken into the compressor where it is pressurized, and it is not only the pressure but the temperature of the air also increases, isn't it? The heat of compression that is added to the air, so that's why along with the pressure the temperature of the air also increases. This high pressure and high temperature air then enters into the combustion chamber where we add the fuel and it is burned at the constant pressure. Okay, so it also means that the heat addition in this open cycle gas turbine plant that takes place at constant pressure. So it is the isobaric heat addition, right? These high temperature gases then enter into the turbine, that is nothing but the condition 3. They expand to the atmospheric pressure, that is the initial pressure, and while carrying out this expansion they produce the mechanical work, that is the power output. Okay, so this W net which is shown here, so that is nothing but the net mechanical work that can be obtained from the arrangement of this gas turbine plant. And as compressor and turbine both are mounted on the same shaft, right? So some of the power output that is used to drive the compressor. Okay, I should take the attention for all of these words, that part of the work which is developed by the turbine that is utilized for the operation of the compressor. Okay, the exhaust gases leaving the turbine are not recirculated. Okay, they are thrown out to the surrounding, they are exhausted to the surrounding and causing the cycle to be identified, known as the open cycle. Another arrangement that I mentioned is a closed cycle gas turbine plant. I can see that the compressor and turbine are similar to what that we have seen for the open cycle arrangement. They are mounted on the one single horizontal shaft and the different state points. Okay, 1, 2, 3, 4. So I would like to draw your attention for the compression and the expansion process that remain the same. Okay, so whatever the way in which this compression expansion was taking place in the open cycle, same happens there in the closed cycle gas turbine power plant as well. But the point to be noted here is that the combustion process, okay, the process 2-3, the combustion process here is replaced by a constant pressure heat addition process from an external source. So you can see that the heat exchanger is placed there instead of a combustion chamber, right? Similarly, the exhaust process that is replaced by a constant pressure heat rejection process to the ambient air. One can also identify here that the heat exchanger is placed there. Okay, so that way the differences can be mentioned, can be given for the open cycle arrangement and the closed cycle arrangement for the gas turbine. The thermodynamic cycle. The thermodynamic cycle is identified as a Breton cycle. Okay, so this cycle is commonly used for the operation of the gas turbine power plants. The layout for the gas turbine power plant that we have seen in the earlier slides, right? Whereas the cycle consisting of the 4 different processes, process 1, 2, process 2, 3, 3, 4 and 4, 1. So these processes are represented schematically on the pressure volume diagram on the left hand side, and the temperature entropy diagram they are on the right hand side. The 4 processes in the sequence: the adiabatic compression process, process 1 to 2, If we see on the temperature entropy diagram, the process 1, 2, so entropy is constant. Entropy at point 1 that is equal to entropy at point 2. So it is essentially an asentropic compression process 1, 2. Okay, for the air. The process 2, 3, if I look there for the pressure volume diagram, I can clearly identify that the pressure at point 2 that is equal to pressure at point 3. So it is a constant pressure, isobaric process. Okay, process 2 to 3 is a constant pressure process, an isobaric process. And if I have a close look on the temperature entropy diagram for the process 2, 3, I can definitely identify that there is a tremendous rise in the temperature from T2 to the T3. Okay, so that way it is nothing but the heat addition at constant pressure. The process 2, 3, constant pressure heat addition. The maximum temperature, the highest temperature in the cycle, so that can be seen on the temperature entropy diagram, and that is at point 3, right? The gases which enters into the turbine. Okay, so that is nothing but the temperature which is the maximum temperature in the cycle. Okay, so the process 3, 4 is the adiabatic expansion process, right? It is also seen that the entropy during the process 3, 4 that is also constant. So it is a asentropic expansion. Okay, so point to be noted here is that the compression and the expansion, both processes are the asentropic processes. Asentropic compression, asentropic expansion. Coming back to the last process, the process 4.1. If I see there on the pressure volume diagram, okay, pressure at point 4 and pressure at point 1, okay, it is the same pressure. So this is again a constant pressure process, an isobaric process. And there is a substantial drop in the temperature from T4 to the T1. Okay, so it is nothing but the constant pressure heat rejection, isobaric heat rejection. Gases are left to the surrounding. Okay, so I hope that you have understood the thermodynamic processes represented on the pressure volume as well as the temperature entropy diagram. So here we again list these processes. Process 1, 2, the work done in the compressor, so it is a negative work, okay, as the work is done on the air, on the working fluid. Process 2, 3, the heat addition in the combustion chamber or in the heat exchanger if it is the closed cycle gas turbine plant. Process 3, 4, work which is obtained from the turbine, we call it as a positive work as the work is developed by the system. Process 4, 1, so heat rejected into the atmosphere or the heat exchanger rather, if it is nothing but the closed cycle gas turbine plant. Now, utilizing the fundamentals of the thermodynamics and making an energy balance, one can derive the equation for the thermal efficiency of the Breton cycle, simple gas turbine cycle. I can mention the compressor work M1 into difference of enthalpies after and before compression. Okay, so M1 into H2 minus H1. Similarly, work which is done from the turbine M3 into H3 minus H4 enthalpy before expansion and enthalpy after expansion. For the air standard cycle analysis, M1 equal to M3. But in the actual cycle it means that air and fuel cycle. Okay, we are using the gas as an fuel. So M3 that is equal to M1 plus MF. MF is nothing but the mass of the fuel which is added in the open cycle gas turbine plant. In the closed cycle gas turbine plant, it is M1 that is equal to M3. Okay, so point to be noted for the open cycle gas turbine plant and closed cycle gas turbine plant. The gaseous fuel which is used for the operation of the gas turbine cycle, let us say it is having the calorific value represented as the CV. So CV is the calorific value. Heat addition, so we can write down mass of the fuel burned into the calorific value. So MF into CV. Okay, mass of the fuel which is burned, and if you multiply that with the calorific value of the fuel, so one can get the heat which is added during the heat addition process, the process 2, 3. In the block diagram that we have seen, the net work which is obtained from the turbine or from the cycle, so it can be expressed as turbine work minus the compressor work, isn't it? Because part of the work that is used for the operation of the compressor, so that's why net work is turbine minus the compressor work, right? By rearrangement of the terms for the net work which is done in the cycle as well as the heat which is added in the cycle, so one can obtain the equation for the air standard cycle efficiency of a gas turbine power plant. Similarly, for the Breton cycle, one can obtain the efficiency 1 minus 1 divided by R raised to gamma minus 1 divided by gamma. Okay, so this efficiency equation that tells us the Breton efficiency depends upon the parameter R, that is known as the pressure ratio. Okay, that is P2 divided by P1, pressure after compression divided by pressure before compression. Or we can write down this pressure ratio as pressure P3 divided by the pressure P4, pressure before expansion divided by pressure after expansion. Okay, so Breton cycle efficiency is a function of pressure ratio R, and it is also the function of gamma. It means that it depends upon the nature of the gas as well. Okay, if we get the pressure ratio that is unity, okay, P2 by P1 that is equal to 1, then this equation bit obvious that tells us that the efficiency will be equal to 0, isn't it? So this equation tells us that higher being the pressure ratio, so definitely higher will be the thermal efficiency. So that can be also seen on these curves which are plotted. On y-axis it is the efficiency, on x-axis I can have the pressure ratio, okay, 0, 2, 4, 6, so likewise the different values of the pressure ratio that I have mentioned. And if I go on increasing the pressure ratio, so I can also see that there is increase in the thermal efficiency of the cycle. Okay, so pressure ratio is the one parameter. Another parameter gamma. So I have shown here the two different curves. One curve that is applicable for gamma equal to 1.4, that is nothing but the air, and another gamma equal to 1.66, so which is applicable for the argon. So I can also make an observation that at a constant pressure ratio, okay, let us say pressure ratio 8, and if I compare the values of efficiencies for gamma equal to 1.4 and gamma equal to 1.66, so I can see that the efficiency being higher for the gas which is having the higher value of gamma. Okay, so hence the variation of the efficiency with the pressure ratio for air equal to 1.4 and for monoatomic gas, that is nothing but the argon, 1.66, so they can be seen on this curve, on this arrangement. The gas turbine power plant that offers various advantages which can be listed here as such. Storage of the fuel that require the lesser area and the handling is easy as compared to the steam turbine power plant. Here we see that the coal is used as a fuel, it requires the abundant space for storage. Not only that one, the handling is also complex. You require the different handling devices as far as the operation of the steam turbine power plant is concerned. The cost of maintenance, so that is obviously less because the lesser number of components are there. Cycle is less complex as compared to that of the steam turbine power plant. So that is what the simple in construction. Okay, there is no need for any boiler, any condenser, or any other accessories which are very commonly used for the steam turbine power plant. The cheaper fuels such as the kerosene, paraffin, benzene, or even powdered coal, so they can be used for the operation of the gas turbine power plant, and they are very cheaper than that of an petrol as well as the diesels. Gas turbine power plant can be easily installed. They can be more popular in the areas which are say having the water scarcity, because in the thermal power plant we have seen that we require the tremendous amount of water for generating the steam. We require a lot of water for the condensation of the steam there in the condenser. So such things are not required for the operation of the gas turbine power plant. The pollution which is caused by the gas turbine power plant, that is substantially less as compared to that of the steam turbine power plant, and obviously less water is required. Coming on to the disadvantages, limitations of the gas turbine plant. 66% of the power developed is used to drive the compressor, isn't it? A substantial power, a sizable power, 2/3 of the power that is required only for the operation of the compressor. So that is what a reason to worry when we are going for the gas turbine power plant. So therefore, the efficiency of the gas turbine, so that is low as compared to the steam turbine power plant. The running speed for the gas turbine, so that is in the range of 40,000 to 1 lakh rpm, tremendously high speed. Not only it is high speed, but the temperatures during the combustion, so those are also very high, ranging in the range around 1100 degrees Celsius to 1260 degrees Celsius, 1300 degrees Celsius. So to operate at such tremendously high temperature, you also require some special materials, special metals and alloys for the fabrication, for the manufacturing of the gas turbine power plants, gas turbine power plant parts as such. isn't they should be thermally stable when they are subjected to such high temperature. Okay. Additionally, the high speed that results in the noise from the compressor, so that being an objectionable, that may not be as such a satisfactory thing for the operation of the gas turbine power plant. Okay. So these are some of the points which makes us the interest to start with the gas turbine power plant. As far as this video is concerned, so we have seen what different points that we are going to study in the gas turbine power plant. We have seen the layout for the gas turbine power plant. We also discussed the working principle for the gas turbine power plant, the two different cycles, namely open cycle gas turbine and closed cycle gas turbine plant, that we have seen how they are been different, that also we have discussed. We have extended our discussion for the thermodynamic cycle, that is Breton cycle, the different thermodynamic processes which occurs in some specific sequence, representation of these processes on pressure volume as well as the temperature entropy diagram, and the equation for the thermal efficiency for the Breton cycle. We concluded that the thermal efficiency depends upon the pressure ratio as well as the nature of the gas used for the operation of the gas turbine power plant. And toward the end, we have discussed about the various points which can be considered as an advantages and the disadvantages of the gas turbine power plant. Okay, so we'll stop here as far as this particular session is concerned. In the next session, we will be focusing on the different methods which can be used for the performance improvement of the gas turbine power plant. Thank you very much.